Hello students, welcome to my channel. This video content is mainly for B.Sc Mathematics Honours. This is my second lecture from the chapter Integers or Number Theory, taken from the block Classical Algebra. In the previous lecture, we discussed the first principle of mathematical induction. You can watch that video from the above I button. In today's video, we are going to look at the second principle of mathematical induction and also look at how to prove it. Okay, so let's get started. Second principle of mathematical induction or second principle of induction. Let S be a subset of n. Here n means the set of all natural numbers, that is n equal to 1, 2, 3, ... Okay, let S be a subset of n such that 1 belongs to S and 1, 2, ... k belongs to S implies k plus 1 belongs to S. Then S is equal to n. This is the second principle of mathematical induction. Now let's look at how to prove this. To prove S equal to n, what do we have to prove? Notice that we have S subset of n. So to prove S equal to n, we have to prove n subset of S, because we know that S equal to n if and only if S subset of n and n subset of S. Since we have S subset of n, so to prove S equal to n, we have to prove n subset of S. Okay, again, to prove n subset of S, we have to prove n minus S equal to prove n subset of S, we have to prove n minus S equal to what? Suppose this is n and this is S. N subset of S. Clearly, n minus S contains nothing, that is n minus S equal to phi, the empty set or null set. So to prove n subset of S, we have to prove n minus S equal to phi. Okay, now we start the proof. Let t equal to n minus S. We have to prove n minus S equal to phi, that is t equal to phi. We shall show that t equal to phi. Okay, if possible, let t not equal to phi. If possible, let t not equal to phi, that is t is non-empty. Then t is a non-empty subset of n. T is a non-empty subset of n. Why subset? Because t equal to n minus S, and this is equal to the set of all x belongs to n such that x does not belong to S, and this is clearly a subset of n. belongs to n implies subset of n. Okay, so T is a non-empty subset of n, and hence by the well ordering property of n, T has a least element. By the well ordering property of n, T has a least element. Now, what is least element and what is well ordering property of n? Least element. Let S subset of n and A belongs to S. Then A is said to be a least element of S if A less equal to x for all x belongs to S. That is the lowest number of the set S. We can say the least element instead of a least element because least element is unique. For example, the least element of the set S equal to 1, 2, 3 is what? The least element of this set is 1, the lowest number of the set. Okay. Now, what is well ordering property of n? Every non-empty subset of n has a least element. Well ordering property. Every non-empty subset of n has a least element. Every non-empty subset of n has a least element. This is the well ordering property of n. Now come back to the proof. T is a non-empty subset of n, and hence by the well ordering property of n, T has a least element. Say m. Okay. Now from the first given condition we have 1 belongs to S. Since 1 belongs to S and m belongs to T and m belongs to T and T is what? T equal to n minus S. Since 1 belongs to S and m belongs to n minus S, therefore m not equal to 1, m not equal to 1 and m not equal to 1 and m belongs to n. Can we say this? M not equal to 1 and m belongs to n. Suppose this is n and this is S. This is n and this is S. So this is n minus S. We have 1 belongs to S, 1 belongs to S and m belongs to n minus S, m belongs to n minus S. Clearly m not equal to 1, 1 belongs to this and m belongs to this, so m not equal to 1. So we can say m not equal to 1. Again m belongs to n, n minus s. M belongs to n minus s, and this is a subset of n, implies m belongs to n. M belongs to n minus s, and this is subset of n, so m belongs to n. Okay, so we can say m not equal to 1 and m belongs to n. That is m greater than 1 and m belongs to n. M not equal to 1 and m belongs to n. From here we can say m greater than 1 and m belongs to n. Can we say this? M greater than 1. We know that every element of n is greater than or equal to 1. Every natural number is greater than or equal to 1. Since m belongs to n and m not equal to 1, so it must be greater than 1. So we can say m greater than 1. Okay. Now m greater than 1 and m belongs to n means m equal to 2 or 3 or 4 or dot dot dot. That is m minus 1 equal to 1 or 2 or 3 or dot dot dot. Clearly m minus 1 belongs to n. So from here we can say m minus 1 belongs to n. Therefore m minus 1 belongs to n. Okay, hence 1, 2 dot 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 m minus 1 belongs to n. From m minus 1 belongs to n, we can say 1, 2 dot 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 m minus 1 belongs to n, because m minus 1 may be 1 or 2 or 3 or any other natural number. For m equal to 2 it is 1, for m equal to 3 it is 2, for m equal to m it is m minus 1, and all of these belong to n. So we can say 1, 2 dot 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 m minus 1 belongs to n. Okay. Again, since m is the least element of T, since m is the least element of T, therefore 1, 2 dot 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 m minus 1 does not belong to T. Can you say this? M is the least element of T. Since m is the least element of T, it is the lowest number of T, but m minus 1 is less than m. In fact, 1, 2 dot 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 m minus 1 are all less than m, so they do not belong to T. So we can say 1, 2 dot 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 m minus 1 does not belong to T, and hence one, 2 dot 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 m minus 1 belongs to, what can we write here? We have 1, 2 dot 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 m minus 1 belongs to n, but does not belong to T equal to what? T equal to n minus s. 1, 2 dot 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 m minus 1 belongs to n, but does not belong to n minus s. 1, 2 dot 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 m minus 1 belongs to n, but does not belong to n minus s, so must belong to s. So we can say 1, 2 dot 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 m minus 1 belongs to s. Okay. Consequently, by 2, by the condition 2, what will we get here from the second given condition? From the second given condition, 1, 2 dot 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 k belongs to s implies k plus 1 belongs to S. Therefore, 1, 2, dot 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 m minus 1 belongs to S implies m minus 1 plus 1 belongs to S. So we have m minus 1 plus 1 belongs to S. That is, m belongs to S. Okay? Which contradicts the fact that m belongs to, what can we write here? M belongs to S contradicts m belongs to what? Suppose this is n and this is S. So this is n minus S. Clearly, m belongs to S contradicts m belongs to n minus S, because S and n minus S are disjoint. So m belongs to S contradicts m belongs to n minus S, that is m belongs to T. Okay, thus we arrive at a contradiction. So our assumption is wrong, that is T not equal to phi is wrong. Therefore T equal to phi. Okay, now what is T? Here T means n minus S. So we have n minus S equal to phi. N minus S equal to phi. That is n minus S contains nothing. So n and S look like this. This is n and this is S. Clearly n is contained in S. That is n is a subset of S. Hence n is a subset of S. Okay. Now given that S is a subset of n, since S is a subset of n, it follows that S equal to n. S subset of n and n subset of S implies S equal to n. Okay, this completes the proof. So we have proved the second principle of mathematical induction. Now let's look at its corollary. Okay, so here is the corollary. Let Pn be a statement involving n. Here statement involving n means what? Let me explain with some examples. We know that 1 square plus 2 square plus 3 square plus dot 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 plus n square equal to, this is equal to what? N into n plus 1 into 2n plus 1 by 6. This is a statement involving n, and this statement is true for all natural numbers n. We can call it Pn. So Pn is the statement 1 square plus 2 square plus 3 square plus dot 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 plus n square equal to n into n plus 1 into 2n plus 1 by 6, and Pn is true for all natural numbers n. Now let's look at another example. 5 to the power 2n minus 1 is divisible by 24. This is a statement involving n, and this statement is true for all natural numbers n. Okay, now come back to the corollary. Let Pn be a statement involving n such that P1 is true and P1, P2 dot 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 Pk are true, implies Pk plus 1 is true. Then Pn is true for all n belongs to n, that is for all natural numbers n. Okay, this is the corollary of the second principle of mathematical induction. Now let's look at how to prove this. First of all, we have to take a suitable subset S of n such that S satisfies the two conditions of the second principle of mathematical induction. Let S equal to the set of all n belongs to n such that Pn is true. Then S is a subset of n. Why subset? Because here we have belongs to n, so S is a subset of n. Okay, then S is a subset of n such that now we have to check whether S satisfies the two conditions of the second principle of mathematical induction. That is, we have to check whether 1 belongs to S and 1 2 dot 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 k belongs to S implies k plus 1 belongs to S. Okay, notice that from the first given condition we have P1 is true, so we can say 1 belongs to S, because Pn is true implies n belongs to S, so P1 is true implies 1 belongs to S, so we have 1 belongs to S, and this is obtained from the first given condition, that is obtained by the condition 1. Okay, so S is a subset of n such that number 1 belongs to S, and number 2 1 2 dot 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 k belongs to S implies, what will we get here? 1 2 dot 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 k belongs to S implies what? From here 1 belongs to S implies P1 is true, 2 belongs to S implies P2 is true, k belongs to S implies Pk is true. So 1 2 dot 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 k belongs to S implies P1 P2 P dot 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 Pk are true. Okay, so 1 2 dot 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 k belongs to S implies P1 P2 dot 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 Pk are true, and this implies what? P1 P2 dot 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 Pk are true implies what? From the second given condition we have P1 P2 dot 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 Pk are true implies Pk plus 1 is true, so this implies Pk plus 1 is true. Again from here Pk plus 1 is true implies k plus 1 belongs to S. So this implies k plus 1 belongs to S. Okay, so 1 2 dot 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 k belongs to S implies k plus 1 belongs to S. So here we have k plus 1 belongs to S, and this is obtained by the second given condition, that is by the condition 2. Thus S is a subset of N such that number 1 belongs to S, and number 2 1 2 dot 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 k belongs to S implies k plus 1 belongs to S. Clearly S satisfies the two conditions of the second principle of mathematical induction. This is the first condition and this is the second condition. Okay, therefore by the second principle of mathematical induction, what can we write here? S equal to N. Okay, now N belongs to N implies N belongs to S, because we have S equal to N. So N belongs to N implies N belongs to S. Okay, and this implies what? N belongs to S implies Pn is true. So this implies Pn is true. Thus N belongs to N implies Pn is true. That is, Pn is true for all N belongs to N. Hence Pn is true for all N belongs to N. Okay, this completes the proof. Alright, so that's it. If you haven't watched my previous lecture, please watch it from the above I button so that you can see the similarities between the proofs of the first and second principle of mathematical induction. If you have any questions, you can ask me freely in the comment section and I will definitely try to answer them. If you like this video, please click on the like button and also subscribe to my channel for more videos which are important for B.Sc Mathematics Honours exam. And don't forget to click on the bell icon that will give you notifications when new videos come out. So thank you so much for watching, and until next time,